Hello students, welcome back. Let us resume our discussion on local extrema. This is the first problem we did. It was an easy one. Here's the graph. We expect local maximum here, local minimum here, increasing, decreasing, and increasing. And then taking the derivative and setting it equal to 0, we get a quadratic equation. Factor and solve, we get 1/3 and -1. Local minimum at 1/3, local maximum at -1, and so on and so forth. Yeah, that wasn't too bad. How about the next problem here? Pretty much the same. Plot first. We expect local minimum here, and then neither maximum nor minimum here. Take the derivative, set it equal to 0. You get cubic equation, but you can factor it. There's a GCF, and then the rest is quadratic. So we have local minimum at x equal to 0, neither maximum nor minimum at x equals to 1, so decreasing and increasing. Now, do you recall this problem? Plot first. We have square root function, so we have only left-hand side. To the right, inside of the square root is negative, so that's invalid. And then take the derivative and set it equal to 0 to find this point here, around x equal to 6. We'll see. Take the derivative using the product rule, good. And then we have this negative power, and then 1/2. Those are denominators. So multiply denominator to each. That'll kill off all the square root, and you end up with a linear equation. You get a critical number 6, so local maximum there, increasing and decreasing. And this is the last problem we did. Again, plot it. We expect a local minimum here, local maximum there, and then decreasing, increasing, decreasing. Now take the derivative and set it equal to 0. Again, use the product rule. And then we have negative power here and 2, so that's the denominator, kill it off, so multiply all those. And then that's going to eliminate all the square root, and then you end up with a quadratic equation. Simplify and solve, you get plus or minus square root of 9/2, or 3 over square root of 2, plus or minus 2.12 something. Yeah, a little bit bigger than 2, symmetrically there. So we get this conclusion. Local minimum, local maximum, decreasing, increasing, decreasing. Okay, how about the next problem here? Excuse me, let me copy and paste this. Okay, let's see. Where's the graph? And then this time, let me copy and paste this. Let's replace this capital E. And then, all right, we get this kind of graph. Let's see, horizontal asymptote, they're going to 0 over there. And local maximum here, local minimum here, decreasing, increasing, decreasing. Okay, that's what I anticipate. Now let's take the derivative and set it equal to 0, and that's going to be a bit of a challenge here. We have to use a product rule, but also chain rule. Derivative of the first function times the second function, this exponential, plus first function times the derivative of the second function, but exponential always remains the same. And then you have to multiply the derivative of the inside. That's the derivative of negative x squared, so this is negative 2x. And that's equal to 0. Okay, all right. How do you solve it? Don't be intimidated. We have common factor exponential. I can factor it out. And then what's left is 1 minus 2x squared. 1 here, or even if you have nothing, everything goes out, then you have 1, and x times negative 2x. So 1 minus 2x squared is equal to 0. Now, exponential is never 0. It's always positive. So this factor has to be 0. 1 minus 2x squared is equal to 0. From there, what do you get? X squared is 1/2. Is that right? That should be right. Therefore, x is 1 over square root of 2, but plus or minus of that. And then look at this symmetry. Around here, around there. Does it make sense? Let's put some space in between so that I can read better. This one too. Now, let's put those into conclusion. So local minimum at x equals to negative 1 over square root of 2. Local maximum at x equals to 1 over positive 1 over square root of 2. And by the way, this quantity is approximately equal to, let's see, 0.7 something, and then this one is positive 0.7 something. Let's go back. 1 is here, 0.7 something. Okay, that makes sense. Okay, so decreasing from negative infinity to negative 1 over square root of 2, increasing from negative 1 over square root of 2 to positive 1 over square root of 2, decreasing from 1 over square root of 2 to infinity. That's the conclusion, and here's a graph. Okay, I'll harder derivative computation, product rule, and factoring out. Here's one more. X cubed times e to the negative x squared. Kind of like this versus that. So I'll employ the same technique. I'll show you the graph and show you some derivative, but left is up to the students. So this is x to the third power times the exponential. So here's the graph. So we have horizontal asymptote, and then local minimum, local maximum. Here, neither maximum nor minimum. Take the derivative and set it equal to 0. And let's take the derivative. Derivative of the first function, 3x squared, times the second function. And then this one, x to the third power, stays the same. And then by the chain rule, exponential stays the same. Derivative of the inside, okay, all right, that's the same derivative computation. Now, what do I do here? And then, what conclusion do I get? Well, local minimum at something, local maximum at something, and by symmetry, positive, negative, you can clearly see that. And then, of course, neither maximum nor minimum at x equal to 0. So decreasing from negative infinity to something, increasing from that to this, and decreasing again from somewhere to infinity. And your job is to find that question mark. And that comes from here. Well, I'll leave you there. Do you have enough time for more? Let's see, how about this one? Okay, all right. Copy and paste this thing. And then I'll show you a graph. Of course, not this graph, the one with the logarithm. And then log x to the 4th power plus 27. And then let's go from negative 5 to positive 5. We have something like this. I don't know, it's really hard to see what is going on here. Interesting. Oh, this part is really flat. Wow, it's really flat. So looks like this is a critical point. Let's go back to negative 5 to positive 5. So, okay, all right, looks like you have a local minimum here, decreasing and increasing. Okay, take the derivative and set it equal to 0. What's the derivative? It's a log function. So remember the derivative of log function? 1 over, that's reciprocal, and by chain rule, whatever inside goes in there. 4th power plus 27. And by chain rule, we have to multiply the derivative of the inside. 4x to the 3rd power and a plus 0. But the multiplication applies to the numerator, so 4x to the 3rd power, that's the derivative computation. And set it equal to 0, and oh boy, this is too simple. You're gonna get x equal to 0. So that's the only critical point, because denominator is always positive. X to the 4th power plus 27 doesn't do much. And then the conclusion is, yeah, counterbalance with the graph. We have local minimum at x equal to 0. Nothing else. And then decreasing in negative infinity to 0, and increasing from 0 to infinity. Okay, it's pretty clear. It's much easier than the previous problem. Why did I write it in part G of all things, actually? Maybe I just copied from the textbook. I don't remember doing that, as a matter of fact. The final problem here, trigonometric function, well, I think this problem is worthy. So let's do this problem in a separate video. Part H.